Hello everyone. This is going to be a mini tutorial on covalent bonds and how to draw the molecules that result from those bonds. We're going to review a couple things that hopefully you already know and have encountered somewhere else, and then we will explore the examples that you can see up here in order to find and understand why we get single, double, and triple covalent bonds depending on the molecule and the atoms in question. All right, couple assumptions. This video assumes you are familiar with the idea of metals and nonmetals. For handy reference here, I put in and highlighted our nonmetals. This also assumes you have encountered the idea that covalent bonds form when two nonmetals meet each other. Some potentially new information, depending on what you've seen before this video, is the octet rule. This is the rule that is a generalization, and there are exceptions, that most atoms, elements on the periodic table, are most stable, or they want, if they could have feelings, 8 valence electrons in their outermost shell. It's a bit redundant. Valence electrons means the outermost electrons, but to bring it home, we're talking about those outermost electrons. The one exception that is definitely relevant for this video, and you will see a lot in chemistry, is a duet exception for hydrogen. Hydrogen fills its outermost, its only shell, with just 2 electrons. So hydrogen only wants 2 total valence electrons. All right, so we're going to look at each one of these one at a time. Chlorine and fluorine, oxygen and fluorine, nitrogen and fluorine, carbon and fluorine, sulfur and oxygen, phosphorus and nitrogen. For each of these first 4, we're going to see examples of single bonds. And you can see the trend already that we're requiring more fluorine in each of these scenarios as we move from chlorine to oxygen to nitrogen to carbon when bonded with fluorine each time. And then we're going to see an example of a double bond and a triple bond. So I'm going to keep changing colors here to keep them simple. One other assumption that this video has is that you are comfortable with the number of valence electrons any of our nonmetals have. And that is real quick. If you count from the left to the right and you skip over the transition metals, you go 1, 2, 3, 4, 5, 6, 7, and 8. The 8 is irrelevant, so I'm going to back up 1. Those are the number of valence electrons for any of the nonmetals that we care about. You can even get rid of boron. And we'll just focus on these here. This also assumes you are comfortable with Lewis dot structures, and you'll see examples of those as we go. All right, so to look at our first example here, chlorine meets fluorine. All right, so chlorine. So first thing you want to do is find out how many valence electrons they have. Chlorine has 7, fluorine has 7. They both have 7 valence electrons. If we're thinking the octet rule, they are both 1 valence electron away from meeting their needs. If I draw my chlorine with its typical Lewis dot structure, you see 1 lone pair, 2 lone pair, 3 lone pairs, and 1 valence electron all by itself. If I switch to drawing fluorine, 1, 2, 3, 4, 5, 6, and it's 7th. These two can bond together. Unlike an ionic bond where we get transfer of valence electrons, covalent bonds are going to share. So they will come together like so. Now this could be done. Many books will teach drawing covalent bonds just like this. I do want to layer on one thing that you commonly see, which is instead of showing the two dots next to each other like that, they will often draw a line over them to hide them. So you've got all the lone pairs remaining on chlorine and a single covalent bond that really is two valence electrons inside, one that is shared from fluorine, one that is shared from chlorine. Fluorine has its 2, 4, 6 in lone pairs, as well as the 7 and 8 found here. So each of them gets to count those electrons that are in the middle. Chlorine has 2, 4, 6, 8. Fluorine has 2, 4, 6, 8 valence electrons. They both satisfy the octet rule. Let's get a teeny bit more complicated. Let's look at oxygen and fluorine. All right, so figure out how many valence electrons they have. Oxygen is over here, trace it up. Oxygen has 6 valence electrons. Fluorine here, trace it up. They've got 7. So 6 and 7. But I do have 2 fluorines now, so 2 of them that have 7 valence electrons. I'm going to draw the one that has more, or less valence electrons first. And then I'm going to position my fluorines around it so that they could interact with one of the unpaired valence electrons around oxygen. So this fluorine can come in and pair up with oxygen's its unpaired valence electron, and then we could replace those dots with a line. I have 2 fluorines, so I need to draw one more fluorine with its unpaired valence electron and its lone pairs. That fluorine will come in, pair up with oxygen's unpaired, and replace those dots with a line. Do your accounting real quick. Do they satisfy the octet rule? Well, here's oxygen. Remembering that a line counts for 2 valence electrons, we've got 2, 4, 6, 8. If we switch to fluorine, well, fluorine has 2, 4, 6, and 8. 2, 4, 6, 8 satisfies the octet rule. All right. Moving a little faster since I think hoping you're getting the trend here. Nitrogen, if we find nitrogen here, trace up, we've got 5 valence electrons, while fluorine still has 7. So nitrogen with its 5 valence electrons, fluorine with 7 each. Draw your nitrogen since it has fewer valence electrons, therefore it can have more bonds first. Then draw your fluorines. 6 and 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. I animatedly move them in to pair them up. Take those unpaired valence electrons and make them a pair. Replace the dots with a line. You get NH3, or sorry, NF3, 3 single bonds. Let's look at CF4. Carbon's right here, trace it up, 4 valence electrons. Carbon has 4, fluorine still has 7. So let's draw carbon first, so it has the most possible bonds, and give it lots of room on all 4 sides. 1 lone electron, 2 unpaired, 3 unpaired, 4 unpaired electrons for carbon. Then we've got fluorine, 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 and fluorine. 4 fluorines present. Starting to get the hang of it, you can start by tracing it out like that, then fill in the lone pairs, all the valence electrons that are pre-paired up. No need to involve carbon, they are already paired. And voila. 1 covalent, 2 covalent, 3 covalent, 4 single covalent bonds, CF4. All right, so these are all still basically continuations of the theme. All right, single bonds to satisfy the octet rule of everybody. Remembering that you're counting a line for 2, and you can satisfy the octet this way. The last 2 that are here are going to require a little bit more creative thinking. If we look at sulfur and oxygen, well, sulfur and oxygen, sulfur's here and has 6 valence electrons. Oxygen is here and has 6 valence electrons. And we only have 1 sulfur and 1 oxygen. So we gotta be a little more creative. Sulfur with 6, oxygen with, no, so used to saying 7, 6 valence electrons. Let's make a single covalent bond first, and we'll see, well, that's not going to work. Single covalent bonds have only allowed us to increase by 1 valence electron. If we do sulfur, 1, 2, 3, 4, 5, and 6. Okay. Let's go oxygen. 1, 2, 3, 4, 5, 6. Well, we can do what we've done before, and that still starts to work. Move the oxygen in, replace the 2 dots with 1 solid line, but do our accounting. And we've got 2, 4, 6, only 7. Sulfur has 2, 4, 6, 7. So we went from 6 to 7, but want to hit the octet rule, we need to go a little bit further. And thankfully, we can see that there are still some unpaired valence electrons. So what you'll do in your mind, and then just represent with a line on the drawing, can move that over there. And move that over there. And then, just like we have done before, replace those two with a solid line. And now, via a double covalent bond, we can get 8. If you look at the accounting for this one, sulfur has 2, 4, 6, and 8. Same accounting is going to work for oxygen with those shared electrons. 2, 4, 6, and 8. Octet rule satisfied. Let's look at the last one. If you're comfortable with the rest so far, this one's going to be cake. It's different, but it's just a continuation of the theme. So nitrogen is up here with 5 valence electrons. Phosphorus is here with 5 valence electrons. Write them in. They are both 5. And let's look at them when they pair up. So we've got phosphorus with 1, 2, 3, 4, 5 valence electrons. We've got nitrogen with 1, 2, 3, 4, 5 valence electrons. If I move this nitrogen in to create a single bond, we're getting closer. Phosphorus, phosphorus has 2, 3, 4, 5, 6. So we went from 5 to 6. I don't know why I said nitrogen has 6 valence electrons. Nitrogen is right here and has 5. Alright, and nitrogen went from the original 5 to 1, 2, 4, 6. So we increased it. We got better. But follow the same theme we did before. Essentially, you can imagine a line from here and a line from here. We get a triple bond. I think that is ugly, 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 so I'm going to backtrack that for a moment and do the more tedious version I was doing before. Bring that in. Bring that in. Bring that valence electron in. Bring that valence electron in. Pair them up with a line. Pair them up with a line. And there's a much nicer looking triple bond. Once you get used to this, there is no need to do the dots under the line. You can just draw them. All right. P, N, 1, 2, 3, triple bond. S, O, double bond. C, F, 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 do 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 do. Single, 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 4 single covalent bonds. So you'll get the hang of this. You'll move it a lot. It'll move a lot faster. Good luck. I hope that helped.